Hey guys, in this video I'm going to be showing you how to calculate the velocity of this disk which is rolling up this slope. And in particular I'm going to calculate the velocity of this disk when it's at this point at the very top of this circular path just here. So pause the video, have a shot at this yourself first, and come back when you're done. Okay, well, hopefully you've attempted the problem the same way I'm about to do it, and that's through energy methods. And if you were to attempt this problem using energy methods, you'd end up using the formula: the change in mechanical energy is equal to the work done by non-conservative forces, right? And what is the work done by non-conservative forces? Let's consider that, and let's consider that by viewing this disk at some point midway through rolling up this circular path. So let's do that. This is our disk just here. This is our disk. We've got three forces on it. We've got our force due to gravity, always acting downwards, mg. We've got our normal force, which is going to be acting perpendicular to our path, which I'll call n. And we've got our friction force here. Easy to overlook, but it's very important. We've got our friction force just here, and we must have a friction force, because without friction, this disk wouldn't be rolling, and rolling was one of the conditions of the question, so there must be a friction force. Okay, so now let's consider the work done by the non-conservative forces. These two, bingo, are the non-conservative forces, but they both do no work. Recall that work is your force times by the distance moved in the direction of your force, right? So the work done by your normal force is going to be 0, because the normal force is always going to be perpendicular to your movement of your center of mass of your disk, right? And the work done by your frictional force is going to be 0, because the point in contact with the ground is going to have an instantaneous velocity of 0, which I've shown in a previous video, which means that this point is not moving in the direction of your friction force, meaning that the work done by your friction force is going to be 0 as well. So that's really just a fancy way of getting to the conclusion that your work done by your non-conservative forces is 0, meaning that we can now figure out the left-hand side of this equation. Alright, let's do that. Alright, what's the left-hand side of this equation? Well, we know the left-hand side can be split into the change in kinetic energy plus the change in potential energy is going to be equal to 0. Okay, so let's see if we can split this into any further pieces. Well, we know because the disk is rolling that it's going to be split into our translational kinetic energy, a half mv2 squared minus v1 squared, and our rotational kinetic energy, a half IO omega 2 squared minus omega 1 squared plus mg h2 minus h1. So to make that a little bit clearer, let me just draw this. This will be our translational movement, and this will be your rotational kinetic energy. Right? So your translational movement refers to your velocity of your center of mass, whereas your rotational movement refers to the angular velocities of your disk. Okay, so let's see if we can solve for these particular types of values. First of all, I'm going to give this to you, even though I've proven in a previous video, that the moment of inertia of a disk rotating around its center point is going to be equal to your mass of your disk times by your radius of your disk squared divided by 2. This is only for a disk. This is for a disk about O. So, and to make you clear about what I mean by O, I'm talking about if this is your disk, that point here is O just there. So, and to make this a little bit clearer, this is a disk, three-dimensional disk, like that. Okay, so that's what I is, just there. Okay, now this becomes a matter of solving for V1, V2, omega 1, omega 2, H2, and H1. So let's do this. First of all, V2, we have no idea what that is. That's what we're trying to solve. But we do know what V1 is. We know that's just 30 meters per second. I wrote that in the question. Okay, now what is omega 2 and what is omega 1? Well, they're tough to figure out, but if you recall from a previous video, I said that if you've got a ball, or disk actually, rolling along a floor in a condition of pure roll, so it's not sliding, it's just rolling, and its center of mass is moving with a velocity v0, that means that its angular velocity omega must be given by the condition that VO is equal to r omega, where r is your radius of your disk, r just there. Okay, this is a formula I proved in a previous video. Don't confuse that with the formula for circular motion. They're very similar, but they're different. So, so that we can use this formula now to find out what omega 2 is. Well, at omega 2, our velocity will be v2, so we can write this as v2 on r, and we can write omega 1 as v1 on r, right? Because the radius of our disk is fixed, so r is going to be the same in both of these cases. Alright, well, that's all well and good, but we're still missing h2 and h1. What are these? What are these? Well, in order to do this, let me copy down our little picture again. Oh. Alright, so here's the diagram showing all the geometries which we're going to be using. I'm going to now create an axis in order to figure out what h1 and h2 are. So I'm going to choose an axis to be right here at this point. I could have chosen any point I liked, but I'm going to choose this point. And if I choose this to be my axis, that means this is going to be x. That means this is going to be y just here, right? Which means, based off our definition of our axis, h1 is going to be 0, right? It's not going to be exactly 0. Technically, h1 will be a positive this distance right here, which I'm drawing in blue. But considering our radius of our disk, 0.2 meters, is so much smaller than the radius of our curvature of our path, 25 meters, it's approximately 0. And it really simplifies our calculations out too. So it's really easy to just say h1 is just 0, right? Now let's find h2. h2 will be this distance here. Not the one I'm doing in dotted red, but this distance just here. From here to here, h2. It's our vertical distance, right? So from our axis. So h2 is this distance. In order to figure that out, let me just draw it slightly larger to the right. So this right now is just a much larger picture of our circular path. This right here is our axis just here. Let me just draw that in green so you see that. This is our axis. This right here is our little red dotted line. This is 45 degrees. This is 45 degrees. We know this is 25 meters, meaning that we know that this distance from here to here is actually just 25 cosine 45, right? That's this vertical distance of our triangle just here, right? And because we know that the distance from here to here is 25 meters, that means we can infer that this distance, which I'm drawing in red, must be, let me just draw that down below, that's going to be 25 minus 25 cosine 45. And if you plug that into your calculator, you're left with h2 is going to be equal to 7.3223 meters. Okay, we're on our way. Now it's just a matter of plugging these values into our formula, which we've got above. So let's do that. In order to do that, let me just copy this formula and put it below. So let's see if I can do that. So let's copy this. Let's copy this and paste it below. There we go. Okay, so let's see. What are our values? Well, we know if we plug all our values in, we're left with a half m v2 squared. Still don't know what that is, so we'll leave it as v2 minus 30 squared, right? Plus a half, remember I0 is just going to be mr squared on 2, mr squared on 2, times by omega 2, and if you recall, omega 2 was just v2 on r, so it's going to be v2 on r squared minus v1 on r all squared, plus mg h2 minus h1, which is going to be, if you scroll up, you can see it. It's going to be 7.3223 minus 0 is going to be equal to 0. Whew, a lot of work, but we're almost there. This just becomes a matter of algebra at this point. So let's actually factor out the v2's just here, and we're left with v2 squared times by a half m. So that's this v2 sorted. So now let's group this v2. Well, it's going to be plus a half times mr squared on 2 times by 1 on r squared. That's this term just here for that v2. And now we're just going to have the rest of it. So we're going to be dealing with this one now, which is going to be minus 30 squared m on 2. And now we're going to be dealing with this term just here, which is going to be minus a half times mr squared on 2 times by v1 squared. I'll just write that as 30 squared on r squared. This is a lot of units to keep in track of, but hopefully I'm not losing you here. Plus mg times by 7.3, I'll just leave it at 7.3 for now, is equal to 0. Okay, a lot of terms, a lot of math, but you'll find that this really simplifies out a whole lot. So let's do the simplification now. Notice that each one of these terms contains mass. That means we can divide mass by both sides, and bam, 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 they all get eliminated. So it's really interesting to note that the mass of your disk is actually not important. Anyway, now it's time to solve for the inside of these brackets. So let's do that. This is going to be v2 squared times by a half, the m's gone, plus a half times by a half. And that's this bracket sorted. That other bit is just this bit. Subtracted from 30 squared on 2, that's this bit. Now let's worry about this bit just here. That's going to be minus 30 squared on 2 times 2, which is 4. Now let's do this last bit, which is going to be plus g times by 7.3223 is going to be equal to 0. Whew, okay, almost done. Now I know I've been saying that all video, but this time I mean it, so let's just power through it. v2 squared times by, well, what's a half plus a quarter? That's going to be 3/4 minus 30 squared times by a half plus a quarter, which is going to be 3/4, plus g times by 7.3223 is equal to 0. And if you bring this term over to the right hand side, and if you bring this term over to the right hand side, you are left with v2 squared times by 3/4 is going to be equal to 30 squared times by 3/4 minus g times 7.3223. And if we multiply both sides by 4/3, we're left with v2 squared is equal to 30 squared times by 3 minus 4g times 7.3223, all divided by 3. And then rather than writing another step out, I'll just square root both sides, and bam, that is the magnitude of the velocity of our disk at its second point. And if we figure out what that equals to, we get v2 is equal to 28.358 meters per second. This is the magnitude of our velocity of our disk at our second point. But remember, we're not done yet. We figured out the magnitude of our velocity. We don't know its direction yet. So let's just quickly redraw the circular arc just here. This is the circular arc. This is the direction of our velocity at our second point. It's going to be in this direction just here. We know that this right here is 45 degrees, meaning we know that this right here is 45 degrees. We know that this is a right angle, meaning that we know this is 45 degrees. So bam, we have our magnitude of our velocity, and we also have our direction. Done. That is our answer right there. Alright, this is our answer. Now let's compare that to a previous question I asked, which was the exact same. So we had a circular path just here, except instead of a disk, we had a block. I've done this in a previous video, and we discussed that for the exact same question, the velocity of our block was actually 27.5 meters per second. Now the only difference between a block undergoing this motion and a disk undergoing this motion is the block doesn't rotate. The disk, however, does rotate. And remember, if we compare these values, they're very similar. V2 here is 28, and here we've got 25. Why does the block have a smaller velocity than the disk, right? And that's because when the disk rolls, and let me just draw a parallel experiment just here so you can actually see. So this is our disk just here with its rolling, and we just proved that it's got a velocity of, what did we say it was? It was 28.36 meters per second, right? Why is the disk got a greater velocity than the block? That's because the disk originally had a greater kinetic energy, because it was not only translating, but it was also rotating. So that means there was more energy to be converted into potential energy. Okay guys, I hope that makes sense. In the next few videos I'm going to be talking about impulse and energy methods.